Okay, let's pursue this regression model equation in a bit more detail. The idea, again, is that we wish to come up with an equation, a mathematical equation for the line, that best fitting line through the scatter plot that we could generate from our dependent and independent x and y coordinate points. Now, we should bear in mind that we can have more than one explanatory or independent variable, more than one x variable. And of course, in that case, it gets very hard to draw on one single scatter plot. So we should recognize that while we get this, and we're starting out with this two-dimensional idea of the relationship between x and y, for multiple regression, cases where we have more than one independent or explanatory variable, we're going to have to think in a little bit more abstract terms because it becomes a multi-dimensional problem. Okay, so here's the idea. We'll start out thinking about what we call simple regression. And in simple regression, we have one y variable and one x variable. And the model equation looks like this. Y is equal to alpha plus beta times x plus epsilon, where y is the value of our response variable for a specific point. I'm calling this a population model, and I'm really thinking about the fact that in a way, we're trying to come up with a general mathematical expression based on a sample of points. So, in essence, this equation is looking at the actual real values of these points that we have. And we're saying the value y of the response variable, that y variable, at any given point is the value we're talking about here. X is the x value of our explanatory variable. So these, for every pair of x and y, we're going to be looking at those points in this data set and in this model equation. The alpha here is the y-intercept. It's the point at which this straight line would cross the y-axis. And beta is the slope of the line, rise over run. This is how much y is increasing for every unit increase of x. Epsilon is an error term because there may be many points, perhaps all the points, that don't actually fall right on that best fitting line. And the vertical distance from each point to the line is what we're going to call the residual or the error term. So for every actual point, the y value is going to be captured by this intercept plus some slope multiplied by the x value. And then there's that error term, how far off the line things fall. Now we're going to try to approximate these values for alpha and beta using the regression analysis, and that's where the inferential statistics comes in. So based on this collection of values of x and y, we're going to try to come up with an inferred, statistically inferred value for as an estimate for alpha and an estimate for beta. And the estimates we come up with are A and B. And this is what's going to lead to a mathematical form that we're more familiar with. So we're going to draw a sample from the population of interest. This will be our collection of points in our data set. We're going to calculate these sample statistics by running our regression analysis and producing this straight line that dissects the sample of data. Now, we'll talk about what that means in a little more detail, but essentially we're trying to find the best fitting line that goes through the middle of the data, goes through the center of the data. And when we capture these estimates for A and B, for alpha and beta, we end up with an expression that says y is equal to a plus b times x, where a is our intercept on the y-axis, is our estimate of alpha, and b is the slope of that straight line. It's the estimate for beta. And there's no error term here because what we're capturing in this case is just the line itself. We're not capturing the actual individual points that fall on either side of the line. So that straight line is going to be sort of our best guess prediction, statistically inferred from this scatter plot, from this collection of x and y values. And you'll remember we said, hey, ultimately, what we want to do is predict a value for y for a specific value of x, and we'll see an example of this. But remember, we said our goal when we don't have all the data is to come up with a best guess and some idea as to how wrong we might be. Well, our best guess, our prediction for y is going to be a plus b times whatever value of x we have. That's going to be our best guess. And then as we'll see from the summary data that we gather in the course of doing the regression analysis, we'll come up with some way of looking at how wrong we might be. And as we'll see, it's in terms that we may recognize from our discussion in the last several blocks of material. So now our task is fitting the data, coming up with that best fitting line. And we're going to systematically draw this best fitting straight line through the points in our scatter plot, through this combination of x and y values. And again, remember, as we go to multiple regression, we'll have more than one dimension of independent variables to think about. But for now, we can still think of this analogy to a scatter plot. Each point on our scatter plot is really characterized by two values. Let me show you what I mean here. I'll bring back in my Java applet here. And imagine this. I've got a scatter plot, a collection of points here on this scatter plot. And there's a line here. Let's say this were the best fitting line. As we'll see in a short while, it's not. But just let's say this were the best fitting line. Well, the y value of each point can be considered as having two components. One here shown in green and one in red. So for every point, the green component is what we call the fitted value. It's the value from some horizontal axis to the line itself. So it's fitted by that best fitting line from the x-axis, wherever that x-axis may be. And the red portion is what we call the residual. That's the vertical distance between the point and that best fitting line. So every point has its y value as a composite of the distance of the line from some horizontal reference, usually the x-axis. In this case, it's not, but usually the x-axis. And then the vertical distance from the point to the line. And that's what we mean by the fitted value and the residual value. Okay, so if we bear this in mind, this will help us see what's going on in the regression analysis. What we're going to do here is something called least squares estimation. We're trying to find the line that minimizes those residuals, the distance between the point and the best fitting line for every single point. Okay, let me bring back in this applet. You'll see that the red lines are what we're calling our residuals, the distance between the point and this best fitting line. And you'll see that in some cases the residuals are large, in some cases they're small. Well, the residuals will never all go to zero unless every single point falls exactly on the line. But if we can adjust this line, we can try to find the line, that combination of a and b in that mathematical expression, y equals a plus b times x. We can find the combination of a and b that give us the smallest overall residuals on average or aggregated across all of the data points. And that's what we try to do in regression analysis. So we want to make these vertical distances as small as possible. And there are a couple of ways we can do this. Remember, we want the best fitting line through the center of the data. And if we think back to our original discussion of summary measures, there's three ways to look at the center, right? When we talked about what's the center of the values in a certain variable, we came up with three approaches: the mean, the median, and the mode. And if you remember those definitions, we can apply the same kind of ideas to deciding what's the best fitting line through our collection of points. Okay? Is it the line that runs directly over the largest number of points? That might be corresponding to the modal approach. So it's the line that actually hits the most points in the scatter plot. Another approach would be to say, hey, I want to find the line that has exactly the same number of points above it and below it. That would be kind of like the median approach. Well, the approach that we take is actually going to be the one that's most like the arithmetic mean, and you'll remember how that's set up for us. We're going to take into account the distances of every point away from the line, and rather than finding the value where those positives and negatives sum exactly to zero, we're going to find the point where they have the smallest total value. And because we have positive and negative residuals, because some points fall above the line, some points fall below the line, we're going to square those residual values so that we're talking about positive numbers in general. And we're going to add them up to get the total amount of squared residuals, the total amount of square error terms in our system. And we want to find the line for which that total value is the smallest. So to go back to our illustration here, and I can click on this line and change the slope of it, kind of pivot it around this midpoint here. But as you can see, for certain lines, the residual values are very large. And this bar on the left-hand side is actually adding up the sum of the error terms, so the lengths of all these red lines squared. So the residuals squared are being summed across all these data points, and that sum is what's shown as the vertical height on this red bar over here. And as I get a line that's a better fit through the center of the data points, that sum of squared residual values decreases. And as we'll see, if I keep going through here, I increase the slope, I increase the slope. At some point, I get to a point where I've gone too far, and now the residuals are increasing again. The magnitudes of some of them are getting so large that sum of square residuals is getting very large again. So the best fitting line is that line that minimizes the sum of those square residual terms. And that comes out somewhere, somewhere around here, pretty close to here. Yeah, I was pretty close. Okay, so this is visually what we mean when we talk about finding that least squares line. So take the square of the residuals, add up those squared residuals, and find the combination of A and B in our mathematical equation that gives us that smallest sum of square residuals. And that process is what we call linear regression, and we can do this in Excel. A few cautionary notes. One of them is causation. We're going to come up with a mathematical equation that links our x value to our y value. It allows us to predict the value of x for any predict the value of y for any value of x. And with a little bit of algebra, we can predict the value of x for any given value of y. What we don't know is anything about the reality of causation. Is the variable x causing the variable y, or is the variable y causing the variable x? Or maybe the two of them just both happen to be related to some other variable that's the actual cause. Well, regression analysis is not the tool that'll give us the information on that. So don't assume causality where there might not be any. The second caution is that, and it's really true of doing inferential statistics in general, we're going to come up with a mathematical equation based on observed values that fall within a certain range. So we're going to come up with a straight line, and the things we can say statistically about that straight line and about the error in our predictions that we might have are really valid just in the range of our data, within the range of the x values we have and the range of y values that we have. So we don't want to go too far away from that. And we'll see a couple of examples that we'll talk about that will make this a bit more concrete. All right, so we'll briefly stop our discussion here, and we'll pick back up with a real example in just a few moments.